Light is the fastest thing in the universe. Nothing can outrun it. At 186,000 miles per second, it circles our entire planet 7.5 times before you finish blinking. It crosses the gap to the moon in just over 1 second. It reaches the sun in 8 minutes. It feels infinite. It feels like the answer to distance. So imagine you could match that speed. Imagine a ship moving at 300,000 kilometers per second, the absolute maximum the laws of physics allow. You would expect the universe to shrink. You would expect every star, every galaxy, every distant world to become reachable. You would be wrong. And the reason why is one of the most disturbing truths in all of science. If you enjoy exploring the edges of what physics actually allows, take a second to hit that like button and subscribe. It genuinely helps the channel more than you might think, and I appreciate every single one of you. Now, brace yourself. Let's begin. There is a fantasy that lives in the mind of every human being who has ever looked up at the night sky and felt the ache of distance. It goes like this. If only we could move fast enough, the universe would open up. The stars would stop being points of light and start being destinations. The galaxies would stop being smudges in a telescope and start being neighborhoods we could visit. Distance, that ancient tormentor, would finally dissolve into speed, and the cosmos would become something we could explore rather than something we could merely observe from a single fragile rock. And the ultimate version of that fantasy, the one that has haunted physicists and dreamers for more than a century, has always centered on a single number, the speed of light. 300,000 kilometers per second, 186,000 miles per second, the fastest speed the universe permits any object or signal to travel. If we could match that number, the thinking goes, we would have conquered distance itself. The stars would bend to our ambition, the galaxies would surrender their secrets, and the terrible isolation of our small blue world would finally end. This episode is built on that fantasy. But it is not an engineering story about propulsion systems or fuel requirements. It is not a speculation about warp drives or fictional shortcuts through space-time. It is something much more uncomfortable than either of those. We are going to do something no spaceship can actually do. We are going to grant you the impossible. We are going to assume, purely for the sake of argument, that you could travel at the full speed of light. The absolute maximum, the cosmic limit, no restrictions, no caveats, pure, uncompromised light speed. And then we are going to watch, distance by distance, target by target, what happens as you point yourself at increasingly remote objects in the cosmos. The results will not match the fantasy, because the speed of light, which feels infinite in every human context you have ever experienced, turns out to be heartbreakingly, almost insultingly slow when measured against the actual dimensions of the universe we inhabit. The fastest speed that physics allows is not fast enough, and that realization is one of the most disturbing truths in all of cosmology. Before that journey begins, one critical point must be stated clearly, because the entire episode depends on understanding it. No object with mass can actually travel at the speed of light. This is not a technological barrier. This is not a limitation waiting to be overcome by better engineering or smarter physicists. This is a structural law embedded in the fabric of space-time itself. Albert Einstein's special theory of relativity, published in 1905, demonstrated that the speed of light is not simply a very high velocity among other velocities. It is a hard wall, a boundary carved into the deepest geometry of reality. Nothing that possesses mass can reach it. Nothing that possesses mass can cross it. And the reason is not negotiable. Here is why. As any object with mass accelerates, the energy required to continue accelerating it increases. At everyday speeds, this effect is so small that it is undetectable. You push a ball, it moves. You push harder, it moves faster. The relationship between force and speed feels perfectly smooth and linear. But at velocities approaching a significant fraction of light speed, that relationship shatters. The energy required to gain each additional increment of speed begins to climb, not gradually, not politely. It climbs with the ferocity of an exponential curve. Physics describes this behavior through a quantity called the Lorentz factor. It is a number that depends on velocity and that governs how dramatically the rules of motion change as speed increases. At rest, the Lorentz factor equals 1. At 50% of light speed, it rises to about 1.15, a modest increase. At 90% of light speed, it climbs to roughly 2.3. At 99%, it jumps to just over 7. At 99.9%, it surges past 22. And as velocity pushes ever closer to 100% of the speed of light, the Lorentz factor does not plateau. It does not level off. It climbs without limit toward infinity. This means that accelerating even a single kilogram of matter to exactly the speed of light would demand an infinite amount of energy. Not an extraordinarily large amount. Truly, mathematically infinite. That quantity of energy does not exist anywhere in the universe. It cannot be gathered, stored, or deployed. The barrier is absolute. This is not just theoretical. It is confirmed every single day in particle accelerators around the world. At facilities like CERN, physicists accelerate subatomic particles to 99.9999% of the speed of light. These particles carry staggering kinetic energy, orders of magnitude more than their rest mass would suggest. But no matter how much energy the accelerators pour into them, the particles never reach 100%. They approach the limit asymptotically, creeping closer and closer but never touching it. The speed of light is not a finish line you can cross with enough determination. It is a wall that pushes back harder the closer you get. Only massless particles can travel at exactly the speed of light. Photons, the particles that carry light itself, are the most familiar example, and they do not have a choice. A photon must travel at that speed from the instant it comes into existence to the instant it is absorbed. It can never slow down. It can never speed up. The speed of light is not a velocity that photons happen to reach. It is the only velocity they are ever permitted to have. So when this episode asks, what would happen if you travelled at light speed, understand that it is asking a purely hypothetical question, a thought experiment designed to test whether the universe's own speed limit, even if you could somehow reach it, would actually be sufficient to make the cosmos feel accessible. We are not asking whether humanity can reach light speed. We cannot. We are asking a deeper and far more unsettling question. We are asking whether light speed itself is enough, whether the fastest possible motion in the universe is adequate for the universe it moves through. The answer is the subject of everything that follows. And the answer, as you will discover, is no. Let us begin where the fantasy still feels alive. Stand on the surface of the Earth and fire a beam of light horizontally along the equator. In one single second, that light circles the entire planet 7.5 times. Not once, not twice. 7.5 complete laps around a world that measures roughly 40,000 kilometers in circumference. A world that Magellan's crew needed 3 brutal years to sail around. A world that the fastest commercial airliners require more than 40 hours of non-stop flight to circumnavigate. Light does it 7.5 times in the space between heartbeats. At this scale, the speed of light does not merely seem fast, it seems omnipotent. It seems like the kind of speed that could reach anything, cross anything, conquer anything that the universe could place in front of it. When you watch light circle the globe 7.5 times in 1 second, you begin to understand why generations of scientists and dreamers have placed all their hope in that number. It looks like the answer to distance. It feels like enough. Now point that beam of light upward, toward the moon. The moon orbits Earth at an average distance of approximately 384,000 kilometers. Light crosses that gap in 1.3 seconds. Just over a single second. During the Apollo missions, when astronauts standing on the lunar surface spoke with mission control in Houston, there was a small but noticeable delay in conversation, roughly 1.3 seconds each way, about 2.5 seconds for a complete round trip, enough to feel slightly awkward, like talking on a video call with a bad connection, but nowhere near enough to cause real trouble. The delay was so modest that most viewers watching the live broadcasts barely noticed it existed. Light speed turned the roughly 384,000 kilometers between Earth and the Moon into a pause shorter than a single breath. IR. The Moon, which took the Apollo astronauts 3 full days to reach in their spacecraft, was conquered by light in barely more than a second. At this distance, light speed still feels absolute. still feels infinite, still feels like far more than enough. Now, aim at the Sun. Our star sits approximately 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, and it serves as the fundamental measuring stick for the entire solar system. Light covers this distance in 8 minutes and 20 seconds. Think carefully about what that number truly means in practice. If the Sun were to suddenly and completely stop producing energy at this exact instant, you would not know for more than 8 minutes. For 8 minutes and 20 seconds, you would continue to see it shining. You would continue to feel its warmth on your face. You would continue casting a shadow. You would live in a world that was, from your perspective, completely normal, illuminated by a star that had already ceased to exist. The sunlight touching your skin right now left the solar surface more than 8 minutes ago. You have never in your life seen the Sun as it currently exists. You have only ever seen it as it was, what it looked like, 8 minutes and 20 seconds in the past. Even light, traveling at the ultimate cosmic speed, introduces a gap between reality and observation at this distance. But 8 minutes still sounds manageable. It is the length of a short commute, the duration of a quick shower. If you boarded a ship moving at the speed of light and aimed it directly at the Sun, you would arrive before a song on the radio finished playing. The fantasy holds. Move deeper into the solar system and the distances begin to stretch, though not yet alarmingly. Mars, at its closest approach to Earth, sits about 55 million kilometers away. Light crosses that gap in roughly 3 minutes. But Mars does not remain close. As both planets orbit the Sun at different speeds and different distances, the gap between them swings dramatically. At its farthest separation, Mars retreats to approximately 400 million kilometers from Earth, and light needs about 22 minutes to make the journey. This is why every Mars rover mission operates with a maddening built-in frustration. When NASA engineers send a command to a rover on the Martian surface, the signal travels at the speed of light and still requires between 6 and 44 minutes for the round trip, depending on where the two planets sit in their respective orbits. Real-time driving is completely impossible. Engineers transmit a command, then sit and wait, hands folded, staring at screens, hoping the rover did not stumble into a crater or lodge a wheel against a rock while the signal was crawling across interplanetary space at 186,000 miles per second. Even at the cosmic speed limit, a conversation with Mars involves minutes of painful, anxious silence. Jupiter, the largest planet in our solar system, orbits the Sun at an average distance of about 778 million kilometers. Sunlight reaches Jupiter in approximately 43 minutes. When the Juno spacecraft orbits Jupiter and sends data home to Earth, the signal travels at light speed and still takes between 32 and 52 minutes to arrive, depending on orbital geometry. Saturn, the ringed giant, sits roughly 1.4 billion kilometers from the Sun. Light requires about 1 hour and 20 minutes to reach it. Uranus, that pale and distant ice giant, receives its sunlight after a journey of approximately 2 hours and 40 minutes. And Neptune, the outermost major planet in our solar system, orbits at roughly 4.5 billion kilometers from the Sun. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. When the New Horizons spacecraft flew past Pluto in July of 2015, the dwarf planet was approximately 5 billion kilometers from Earth. The signal confirming a successful flyby, traveling at the speed of light, took 4 hours and 25 minutes to reach mission control. The team had to wait nearly 4.5 hours to learn whether a decade of meticulous planning and more than 3 billion miles of travel had actually worked. They sat in silence, unable to intervene, unable to help, while the confirmation crawled across the solar system at the fastest speed physics allows. Even at light speed, the outer solar system demands patience measured in hours. But here is what matters about all of these numbers taken together. If you boarded a ship moving at the speed of light and launched from Earth right now, you would pass the Moon in 1.3 seconds. You would reach the Sun 8 minutes later. Mars would fall behind you within minutes. Jupiter within the hour. Saturn before lunch. Neptune before dinner. In a single day of travel at the absolute maximum velocity the universe permits, every known planet in the solar system would be behind you. Light speed makes the solar system feel compact. It makes the planets feel close. It makes the space between the worlds feel like something you could cross during a morning commute. This is where the fantasy is at its strongest. At this scale, light speed genuinely does feel like the answer to distance. But the solar system does not end at Neptune. It does not end at Pluto. It does not even end at the Kuiper belt, that broad ring of icy objects extending from roughly 30 to 50 astronomical units from the Sun. Light crosses the Kuiper belt in a matter of hours. Still manageable, still comfortable, still within the illusion. What lies beyond the Kuiper belt is where our solar system reveals its true and terrifying scale. The Oort cloud is a hypothetical shell of icy debris believed to surround the entire solar system in a vast, roughly spherical enclosure. Scientists estimate it begins at approximately 2,000 astronomical units from the Sun and may extend outward to as far as 100,000 astronomical units. That outermost boundary sits approximately 1.5 light-years from Earth. At the fastest speed anything can travel, reaching the far edge of our own star's gravitational territory would take approximately 18 months, a year and a half. At 300,000 kilometers per second, a year and a half at 186,000 miles per second, a year and a half of continuous travel at the absolute cosmic maximum, and you still have not arrived at another star. You have merely exited the outermost boundary of your own star's domain. You have crossed the threshold where the gravitational influence of the Sun finally fades and the influence of neighbouring stars begins to compete. 18 months at the universal speed limit, and all you have accomplished is leaving home. For perspective, the Voyager 1 spacecraft, after nearly 50 years of flight, has covered barely 23 light hours. The Oort cloud's outer edge is more than 13,000 light hours away. If Voyager 1 were aimed at the far boundary of the Oort cloud, rather than simply drifting outward, it would take roughly 30,000 years to reach it. Even light needs a year and a half. The solar system, which felt so small when light was crossing it in hours, turns out to have an enormous, invisible frontier that extends far beyond everything we normally think of as belonging to our star. This is where the first real crack appears in the fantasy. Not a catastrophic failure, not a dramatic collapse, just a quiet, uncomfortable realization that the distances ahead are constructed on a fundamentally different scale than the distances behind. The entire planetary solar system, from the Sun out to Neptune, fits inside a sphere roughly 8 light hours across. The Oort cloud stretches that sphere to approximately 3 light years, and beyond it sits a destination that will put the fantasy under its first genuine strain. Proxima Centauri is the closest star to our Sun. It is a small, dim red dwarf, only about 12% the mass of our Sun, barely luminous enough to see even through a telescope. It orbits as part of the Alpha Centauri triple star system, the nearest stellar system to our own. Proxima Centauri sits 4.24 light-years from Earth. That distance translates to approximately 40 trillion kilometers. 40 trillion. If you could somehow travel at the full speed of light, reaching Proxima Centauri would take 4 years, 2 months, and roughly 3 weeks. More than 4 years at the absolute maximum velocity any object or signal is permitted to travel. More than 4 years of constant motion at 300,000 kilometers per second to reach the nearest star. To understand what 4 years of light-speed travel truly means, hold it against the scale of a human life. The entire Second World War, from the invasion of Poland in 1939 to the Japanese surrender in 1945, lasted 6 years. A light-speed journey to the nearest star consumes more than 2/3 of that span. A bachelor's degree at most universities takes 4 years. You could complete an entire undergraduate education in the time it takes light to cross the gap between our Sun and its nearest neighbour. A full presidential term in the United States lasts 4 years. An entire administration could rise, govern, and end while your lightspeed ship is still coasting toward the closest star in the sky. And this is the best possible case. This is the minimum interstellar journey. This is the shortest distance between our star and any other star in the galaxy. Everything beyond Proxima Centauri is farther. Most of it is incomparably farther. To feel this distance another way, consider what humanity has actually achieved in terms of speed. The fastest human-made object in history is the Parker Solar Probe, which reached a peak velocity of approximately 692,000 kilometers per hour during its closest solar approach in late 2024. That is roughly 192 kilometers per second, extraordinarily fast by any engineering standard ever set, and it represents about 0.064% of the speed of light. At that speed, reaching Proxima Centauri would take approximately 6,800 years, nearly 7 millennia. The pyramids of Giza were built roughly 4,500 years ago. The Parker Solar Probe, the fastest machine humanity has ever created, would need to fly for longer than the entire age of the pyramids to reach the nearest star. Light does the same journey in just over 4 years. The gap between human engineering and the cosmic speed limit is a factor of more than 1,500. Then there is Voyager 1. Launched in 1977, Voyager 1 is currently the most distant human-made object from Earth. It has been flying continuously through space for nearly half a century. After all that time, after all those years of unbroken travel, it has reached a distance of approximately 165 astronomical units from the Sun. That sounds impressive until you convert it. 165 astronomical units is roughly 23 light hours. Not light years, light hours. Voyager 1 has been soaring through space for close to 50 years and has not yet crossed a single light day. Proxima Centauri is 4.24 light years away. At Voyager 1's current speed, reaching that star would take over 70,000 years. The entire span of recorded human civilization fits within the last 5,000 to 6,000 years. Voyager 1 would need to fly for more than 12 times the length of all recorded history to arrive at the closest neighbouring star. And even after you somehow close the impossible gap between Voyager 1's speed and light speed, even after reaching the full, pure, uncompromised maximum, the trip to the closest star still takes 4 years. To make the distance even more visceral, consider a scale model. Shrink the Sun down to the size of a grapefruit, roughly 10 centimeters across. At that scale, Earth would be a barely visible grain of sand orbiting about 11 meters away. Jupiter would be a small marble, roughly 57 meters from the grapefruit. Neptune would be a pinhead more than 340 meters out. Now ask where Proxima Centauri would be in this model. It would be another, much smaller grapefruit sitting approximately 3,000 kilometers away, not in the next room, not in the next town, not even in the same country. Roughly the distance from one coast of the Mediterranean to the other. That is the gap between our star and the closest neighbouring star, rendered in a model you could hold in your hand. Light crosses that gap in 4 years and 2 months. The fastest spacecraft in history would need nearly 7,000 years. And now consider what 4.24 years of light speed travel means for communication. If a colony of humans somehow established itself on a planet orbiting Proxima Centauri, and you sent them a message from Earth today, that message, travelling at the absolute maximum speed the universe allows, would not arrive for 4 years and 2 months. A reply, also travelling at light speed, would take another 4 years and 2 months to come back. A single round-trip exchange of words would consume more than 8 years. You could send a simple question about conditions on the surface and receive the answer after your children had started secondary school. A back-and-forth negotiation between two governments would require decades to conduct. A meaningful, responsive conversation between Earth and its nearest possible interstellar colony would be generationally impossible. Light speed, the fastest information transfer physics permits, turns even the nearest interstellar dialogue into an exercise in patience beyond anything human civilization has ever demonstrated. Here is the fact that turns the first crack into a fracture. Proxima Centauri is not a distant star. It is not a remote or exotic target at the far side of the galaxy. It is the closest star to our solar system, and it is very nearly the closest star that could exist, given the typical spacing of stars in our region of the Milky Way. The average distance between neighbouring stars in this part of the galaxy is roughly 4 to 5 light years, meaning Proxima Centauri is an almost perfectly average neighbour. But the Milky Way contains somewhere between 100 billion and 400 billion stars spread across a disk, roughly 100,000 light-years in diameter. The overwhelming majority of those stars sit thousands, tens of thousands, or hundreds of thousands of light-years from Earth. If the nearest star, the closest possible destination beyond our own Sun, already takes more than 4 years at the maximum allowed speed, what does the rest of the galaxy look like? What happens when you face a structure not 4 light-years across, but 100,000? Light speed performed magnificently across every scale that humans have ever physically touched. It circled the Earth in a fraction of a second. It crossed the solar system in hours. It conquered every distance any human spacecraft has ever traveled and made it look effortless. It demolished every measurement that our species has ever personally experienced and left the illusion of infinite speed intact. But at the very first step beyond our own star, it stumbled. Not because light slowed down. Light never slows down. It moves at the same constant velocity in every reference frame. Always, everywhere, without exception. It stumbled because the distances ahead are built on a completely different scale than anything behind. The entire planetary solar system fits inside a sphere, roughly 8 light-hours across. The next star is more than 4 light-years away. The ratio between those two distances is roughly 4,000 to 1, and the galaxy stretching beyond that nearest star spans 100,000 light-years from edge to edge. Light speed just faced its first real test outside the solar system, and it passed only by a technicality. The journey to Proxima Centauri is possible in principle but demands years at maximum velocity. It is not the instant, effortless, godlike conquest that the fantasy promised when light circled the Earth 7.5 times per second, and the distances about to come will not be as forgiving. Proxima Centauri was the opening act. It was the easiest interstellar destination the universe could offer. Everything from here forward will make it look like it was sitting right next door. Proxima Centauri took 4 years. 4 years at the fastest speed the universe allows just to reach the closest star. That was the first warning. The solar system had felt like a playground, something light speed could cross during a lunch break. But the gap to the nearest neighbouring star introduced a delay measured not in seconds or minutes but in years. And that was the easiest interstellar journey the cosmos has to offer. Everything beyond Proxima Centauri is farther. Most of it is unimaginably farther. Because the next challenge is not another star. It is the galaxy that contains them all. The Milky Way is our home galaxy. It is a barred spiral structure containing somewhere between 100 billion and 400 billion stars. Every single one of those stars is a sun in its own right, a thermonuclear furnace burning hydrogen into helium, flooding the space around it with light and heat. Many of those suns are orbited by planets. Some of those planets sit in habitable zones where liquid water could exist on their surfaces. The galaxy contains stellar nurseries where new stars ignite from collapsing clouds of gas, and stellar graveyards where dead stars collapse into white dwarfs, neutron stars, and black holes. It contains supernova remnants, planetary nebulae, globular clusters older than the Earth, and a supermassive black hole at its centre, called Sagittarius A star, weighing in at roughly 4 million times the mass of our Sun. All of it, every star, every planet, every cloud of gas, every remnant of every dead star, is held together by gravity into a single rotating disk, roughly 1,000 light-years thick and staggeringly wide. And it is that width, that diameter, that shatters the fantasy of light speed as a vehicle for cosmic exploration. The Milky Way stretches approximately 100,000 light-years from one edge to the other. Some recent estimates push that number higher, perhaps to 150,000 or even 200,000 light-years, when you include the faint outer disk, but the conservative and most widely cited figure remains 100,000. That is the number we will use, 100,000 light-years. It sounds clean, it sounds manageable. It is neither. If you boarded a ship travelling at the speed of light and set off from one edge of the galaxy toward the other, you would arrive at the far side in 100,000 years. Not 100,000 miles. Not 100,000 hours. 100,000 years. At the fastest speed anything can travel, crossing our own galaxy, the one we live in, the one that contains our sun and our planet and every star visible in our night sky, takes longer than the entire history of modern human civilization multiplied by a factor of roughly 20. Consider what 100,000 years means in human terms. The entirety of recorded human history stretches back roughly 5,000 years to the earliest known writing systems in ancient Mesopotamia. The construction of the Great Pyramid at Giza, one of the oldest monumental structures still standing, occurred roughly 4,500 years ago. The Roman Empire rose and fell. The Renaissance came and went. The Industrial Revolution transformed the world. The digital age emerged. All of it, the complete span of every civilization that has ever kept written records, fills approximately 5% of the time light needs to cross the Milky Way. 5%. Every empire, every war, every treaty, every invention, every revolution, every book ever written, every symphony ever performed, every scientific discovery from the lever to the laser, all of it occupies 1/20th of the time it takes light to fly from one edge of our galaxy to the other. To fill the remaining 95%, you would need to repeat the entire saga of recorded human civilization 19 more times, and all 20 repetitions combined would only just barely cover the journey. Go further back. Homo sapiens as a species emerged roughly 300,000 years ago on the plains of Africa. Our entire biological existence, every generation that has ever lived, every migration, every ice age survived, every language invented, every civilization built and collapsed, fits inside 3 galactic crossing times. Light leaving one edge of the Milky Way today would need to travel for 1/3 of the entire existence of our species before it reached the other side. A photon departing the far edge of the galaxy right now, at this very moment, will not arrive at our position for roughly 100,000 years. When it finally reaches Earth, the year will be approximately 102,026. Whatever civilization exists on this planet at that time, if any civilization exists at all, will bear no resemblance to the one hearing these words today. The languages will be unrecognizable. The cultures will be unrecognizable. The species itself may have evolved into something new. That is how long light takes to cross our galaxy. That is the travel time at maximum speed. And while light is making that crossing, the galaxy itself does not hold still. The Milky Way rotates. Every star, every gas cloud, every dark matter halo in the disk orbits the galactic center in a vast, slow carousel. Our own solar system moves through this orbit at a speed of roughly 230 kilometers per second, about 828,000 kilometers per hour. That is fast enough to cross the entire width of the United States in roughly 20 seconds. But even at that staggering orbital velocity, one complete lap around the galactic center takes approximately 225 million years. Astronomers call this period a cosmic year. To feel how long that is, consider that the last time our solar system occupied roughly the same position in its orbit that it occupies right now, dinosaurs were just beginning to emerge on the surface of the Earth. The Triassic period was underway. Mammals did not yet exist. Flowering plants had not yet evolved. An entire era of terrestrial life has unfolded since our last galactic orbit began. Now consider what that timescale means for a light-speed crossing. In the 100,000 years it takes light to travel from one edge of the Milky Way to the other, the galaxy barely even notices. 100,000 years does not register as even 1,000th of a single galactic rotation. A star on the far edge of the disk would drift only slightly along its orbit during the crossing, tens of light years along a circular path that spans well over 100,000. The galaxy is not a photograph frozen in space. It is a spinning, living, dynamic structure, but it moves on timescales so vast that even a 100,000-year light-speed crossing is merely a single heartbeat in galactic time. Our solar system sits roughly 26,000 light-years from the galactic center, embedded in a relatively minor spiral structure called the Orion Arm, sometimes called the local spur. We are not at the center of the galaxy. We are not near the center. We are roughly halfway out along the disk, nestled in a quiet suburban arm, far from the dense, violent core. From our position, a beam of light aimed at the supermassive black hole at the heart of the galaxy, the 4 million solar mass monster known as Sagittarius A star, would take 26,000 years to arrive. 26,000 years. The last ice age ended roughly 11,700 years ago. Agriculture was invented about 10,000 years ago. A light-speed signal from Earth to the center of our own galaxy would take more than twice as long as the entire span of human civilization since we first planted seeds in the ground. And that is not even the far side of the galaxy. That is the center. The full crossing, edge to edge, is nearly 4 times longer still. To feel the absurdity of this scale, consider a thought experiment. Shrink the entire Milky Way galaxy down to the size of a football pitch, roughly 100 meters from end to end. At that scale, how large would our solar system be? Not the size of a marble, not the size of a grain of sand, not even the size of a bacterium. Our entire solar system, from the Sun all the way out to the orbit of Neptune, would be smaller than a single wavelength of visible light. It would be completely invisible, not just to the naked eye, but to any optical microscope ever built. You could search the entire football pitch with the most powerful magnifying glass in existence and never find us. That is the scale of the galaxy relative to everything humans have ever known. We live in a structure so vast that our entire cosmic backyard, the space containing every planet we have ever photographed, every moon we have ever landed on, every comet we have ever tracked, every asteroid we have ever named, would vanish into invisibility if the galaxy were shrunk to the size of a field you could walk across in 90 seconds. At this point in the story, someone always raises a hand. What about time dilation? What about Einstein's other gift to physics? The one that says time slows down for objects moving at extreme velocities. Could that not save us? Could a traveller moving at nearly the speed of light experience the journey in far less time than 100,000 years? Could time dilation turn the galaxy into something a single human being could cross within a lifetime? The short answer is yes, in a narrow and deeply misleading sense. The longer answer is the reason this matters so much. Time dilation is one of the most experimentally verified predictions in all of physics. It emerges directly from Einstein's special theory of relativity, and it has been confirmed repeatedly by precision clocks on aircraft, by measurements of unstable particle lifetimes in accelerators, and by the Global Positioning System satellites orbiting Earth right now, which must correct for relativistic time dilation effects every single day to maintain accurate positioning. Without those corrections, GPS coordinates would drift by roughly 10 kilometers per day. The phenomenon is real. It is not controversial. It is not speculative. And it works exactly as the mathematics predicts. When an object moves at a significant fraction of the speed of light relative to an observer, time passes more slowly for the moving object. The faster the object moves, the more dramatic the slowdown becomes. This is not a perceptual trick. It is not an illusion caused by signal delay or observational bias. The moving object genuinely and physically experiences fewer elapsed seconds than the stationary observer does. Clocks tick slower, hearts beat slower, neurons fire slower, chemical reactions proceed at a reduced rate, aging itself slows down. Every physical and biological process aboard the moving object runs in slow motion relative to the outside universe. From the traveller's own perspective, nothing feels different. A second still feels like a second. A heartbeat still feels like a heartbeat. But when the traveller compares their clock to a stationary clock after the journey, the difference is undeniable. Less time has passed for them. They are younger than they should be. The compression is governed by the Lorentz factor, the same quantity we encountered earlier in this story when we discussed why mass cannot reach light speed. At 90% of the speed of light, the Lorentz factor is roughly 2.3. A traveller at that speed experiences time about 2.3 times slower than an observer at rest. A journey that takes 100,000 years from the stationary perspective would feel like roughly 43,000 years to the traveller. Still absurdly long. Still far beyond a human lifetime. Time dilation at 90% of light speed barely dents the problem. Push faster. At 99% of the speed of light, the Lorentz factor climbs to about 7. The same 100,000-year crossing now feels like roughly 14,000 years to the traveller. Better, still vastly beyond any human lifespan, but significantly compressed. Push faster still. At 99.9% of the speed of light, the Lorentz factor reaches approximately 22. The crossing compresses to roughly 4,500 years of experience time. Still impossible for a single human, but now within the range of a very long-lived civilization. Keep pushing. At 99.99% of light speed, the factor reaches about 71. The galactic crossing shrinks to roughly 1,400 years of personal time. At 99.9999%, the factor soars past 700. The traveler would experience the entire crossing of the Milky Way in about 140 years, getting close to a human lifespan, though still beyond it, and at even more extreme velocities, with enough nines stacked after the decimal point. The experience time could theoretically compress to decades, perhaps even years. Physicists have calculated that if a spacecraft could somehow maintain a constant acceleration of 1g, about the same gravitational pull you feel standing on the surface of the Earth, it could cross the entire Milky Way in roughly 20 to 25 years of onboard time. The traveller would accelerate for the first half of the journey, then flip the ship and decelerate for the second half, arriving at the far edge of the galaxy having aged only a couple of decades. That sounds miraculous. That sounds like the fantasy restored. That sounds like time dilation has solved the problem that light speed created. It has not, and understanding why it has not is the single most important idea in this entire episode. Here is what time dilation actually does. It compresses the traveller's experience. It makes the journey feel shorter for the person inside the ship, but it does absolutely nothing to the outside universe. Not one thing. While the traveller experiences 25 years of pleasant onboard time crossing the galaxy, the rest of the universe ages the full 100,000 years. Every clock on Earth ticks forward 100,000 years. Every calendar advances 100,000 years. Every person the traveller ever knew dies. Their children die. Their grandchildren die. The civilization that launched the ship rises, transforms, declines, and vanishes. The civilization that replaces it does the same, and the one after that, and the one after that. Hundreds of civilizations could rise and fall in 100,000 years. The languages spoken on Earth when the traveller departed are forgotten, replaced by new languages, which are themselves forgotten and replaced dozens of times over. The continents have drifted measurably, coastlines have redrawn themselves, ice ages may have come and gone. The constellations visible in the night sky have rearranged, because stars move, and 100,000 years is long enough for the familiar patterns to distort beyond recognition. 100,000 years of relentless, unbroken history have unfolded, while the traveller sat in a cabin and aged 25 years. The traveller's clock was slow, the universe's clock was not. Time dilation does not shrink the universe. It does not make the galaxy smaller. It does not reduce the distance between stars or compress the structure of space-time. What it does, and all it does, is allow the traveller to skip forward through time. The traveller does not arrive at the far side of the galaxy in 25 years. They arrive 100,000 years in the future, having personally experienced only 25 years. The distinction is critical. The galaxy is still 100,000 light-years across. Light still takes 100,000 years to cross it. The outside universe still ages the full duration. Time dilation simply allows the traveller to be unconscious in effect for most of that duration. It is not a shortcut. It is a one-way ticket to the distant future with no return. And this is where the human cost becomes real. A traveller who crossed the Milky Way using extreme time dilation would step off their ship into a universe that had aged 100,000 years. They could never go back. Even if they turned around immediately and flew back at the same speed, another 100,000 years would pass in the outside universe. The round trip would consume 200,000 years of real cosmic time. The traveller would return to an Earth so changed that it might not be recognizable as the same planet. Time dilation does not defeat the distance. It merely changes who pays the price. Instead of the traveller enduring 100,000 years of boredom, the universe endures 100,000 years of change. The cost is identical. It is simply transferred from the passenger to everything else. This is the trap that time dilation sets. It offers what appears to be a solution and then reveals, quietly, that the solution is worse than the problem it pretends to solve. Because the problem was never that the journey takes too long for the traveller. The problem is that the universe is so large that crossing it requires timescales that erase civilizations, that outlast species, that consume entire geological epochs. Time dilation lets the traveller survive those timescales personally, but it does not prevent them from occurring. The universe outside the ship ages at its normal, unrelenting pace, regardless of how fast the ship moves or how slowly the traveler's personal clock ticks. You can slow your own time to a crawl. You cannot slow the universe's. And that distinction is the difference between a genuine solution and a cruel trick dressed up in elegant mathematics. And remember, everything discussed so far, every crushing number, every impossible timeline, every demonstration of time dilation's cost, applies only to our own galaxy. One single spiral structure among the trillions that populate the observable universe. A single city in an infinite landscape. The distances beyond the Milky Way are worse. They are catastrophically, almost absurdly worse. And they begin with something that is, in its own way, more disturbing than any distance. They begin with emptiness. The space between galaxies is not merely empty in the casual sense that a room is empty when no one is standing in it. Intergalactic space is the most complete void that nature produces. The density of matter between galaxies drops to levels so low that you could fly through millions of cubic kilometers and never encounter a single atom. The temperature hovers just a few degrees above absolute zero, the coldest anything can theoretically be, a whisper above the point where all thermal motion ceases. There is no light except the faint, ancient glow of the cosmic microwave background and the impossibly dim smudges of distant galaxies receding in every direction. No sound, obviously. No structure. No dust. No gas worth measuring. If a traveller at light speed left the outer edge of the Milky Way heading toward our nearest galactic neighbours, they would spend tens of thousands of years crossing a void that contains essentially nothing. Not featureless in the poetic sense, featureless in the physical sense. A vacuum so thorough that individual atoms are separated by distances measured not in millimeters but in meters. This is the medium that separates every galaxy from every other galaxy, and it must be crossed before any intergalactic destination can be reached. The Large Magellanic Cloud is one of the closest satellite galaxies to the Milky Way. It is a small, irregular galaxy containing roughly 30 billion stars, visible to the naked eye from the southern hemisphere as a faint, cloudy smudge against the dark sky. For centuries, southern hemisphere observers used it for celestial navigation, unaware they were looking at a separate galaxy. It sits approximately 160,000 light-years from Earth. At light speed, reaching it would take 160,000 years of outside time. Even with the most extreme time dilation achievable by any near-light-speed traveller, the universe beyond the ship would grind forward through 160,000 years of unbroken change. That is more than half the age of Homo sapiens as a species. An entire human species length of time, consumed and discarded just to reach a small satellite galaxy that is essentially still gravitationally tethered to our own. The small Magellanic Cloud sits roughly 200,000 light-years away. Slightly farther, slightly more punishing. Both of these galaxies orbit the Milky Way like moons orbiting a planet. They are our closest independent galactic companions, the nearest islands in the intergalactic sea, and reaching either one of them at the speed of light requires a journey longer than our species has been alive. The Triangulum Galaxy, the third largest member of our local group, lies roughly 2.7 million light-years away, nearly as far as Andromeda, nearly as devastating to contemplate. Now face the real test. The Andromeda Galaxy, also known as M31, is the nearest large spiral galaxy to the Milky Way. It is a massive structure containing roughly 1 trillion stars, stretching approximately 220,000 light-years across, significantly larger than our own galaxy. On a clear autumn night in the northern hemisphere, you can see it with the naked eye as a faint oval smudge in the constellation Andromeda. That smudge is the most distant object most humans will ever see without a telescope, and its distance from Earth is approximately 2.5 million light-years. 2.5 million light-years. Let that number breathe for a moment. At the speed of light, reaching Andromeda would take 2,500,000 years. When the light you see from Andromeda tonight began its journey toward your eyes, our ancestors had barely begun walking upright on the plains of eastern Africa. They were chipping the earliest stone tools from river cobbles. They had not discovered fire. They had not developed language. The genus Homo was in its infancy, and our specific species, Homo sapiens, would not emerge for another 2 million years. Every single development in all of human existence, from the first controlled flame to the first written word to the first wheel to the first telescope to the spacecraft orbiting other planets right now, occurred while that faint smudge of Andromedan light was silently crossing the void between galaxies. And that is just the light arriving. The journey in the other direction is identical. If a human traveller departed Earth today at the speed of light, aimed directly at Andromeda, they would arrive 2.5 million years from now. Even with time dilation compressing the personal experience into mere decades, the outside universe would age the full 2.5 million years. Earth would grind through geological eras. Continents would drift. Ice ages would come and go. Species would evolve, flourish, and go extinct. The sun would still be burning, barely changed in its output, because stellar lifetimes span billions of years. But the surface of the planet would be unrecognizable. Everything humans ever built would be gone. Every city, every highway, every dam, every monument, every trace of every civilization. 2.5 million years is long enough for rivers to carve new valleys, for coastlines to reshape themselves entirely, for erosion to grind mountains to plains. A departing traveller who somehow turned around and came back would find no home waiting, only geology and silence. But consider the other half of that journey. Consider the arrival. You have crossed 2.5 million light years, or experienced the compressed equivalent through time dilation, and you step off the ship into the Andromeda galaxy. What greets you is not a destination in any meaningful sense. It is an entirely alien structure containing roughly 1 trillion stars, not one of which has ever been observed in detail by human instruments. None of them have names. None of their planets have been catalogued. No map exists for any corner of this galaxy. The constellations in the sky are completely unfamiliar, patterns no human eye has ever seen, because every point of light is a star that belongs to Andromeda rather than the Milky Way. The physics is identical, but the sheer foreignness of the place is absolute. You are standing in a galaxy that no human has ever seen from the inside. No message can reach anyone who cares. No reply can ever come, because the home you left behind has been dead for longer than recorded history. You have not travelled to another place. You have travelled to another world, in another galaxy, in another epoch, and you are utterly, irreversibly alone in it. And Andromeda is close. It is the nearest large galaxy. It is our neighbour, our gravitational companion, and one of only a handful of galaxies near enough to see without a telescope. The local group, the gravitational family of galaxies to which the Milky Way belongs, contains roughly 80 galaxies, spread across approximately 10 million light-years of space. Most of these are small dwarf galaxies containing only a few billion stars each, but together they form a gravitationally bound system, a cosmic neighbourhood where galaxies interact, orbit one another, and occasionally collide. The Milky Way and Andromeda dominate this neighbourhood, and they are currently falling toward each other at roughly 250,000 miles per hour. In approximately 4.5 billion years, they will collide and merge into a single elliptical galaxy. But even that collision, even that immense cosmic event, takes place entirely within the boundaries of the local group, and crossing the local group itself, edge to edge, at the speed of light, takes 10 million years. 10 million years, and you have not left our local galactic neighbourhood. You have not reached the Virgo cluster. You have not approached the cosmic web. You have not touched the edge of the observable universe. You have merely crossed the modest space that separates our galaxy from its closest companions. Time dilation cannot repair what these distances have broken. It was never designed to. It can compress the traveller's experience, shaving millennia to decades on a shipboard clock. But it cannot stop the outside universe from aging. It cannot freeze the civilizations left behind. It cannot pause the erosion of continents or the evolution of species or the slow cooling of stars. At every scale beyond the solar system, the distances demand timescales that dwarf human civilization, human biology, and eventually human comprehension. The speed of light, which circled the Earth 7.5 times per second, which crossed the solar system in a lazy afternoon, is now failing to make even our local galactic neighbourhood feel accessible. And time dilation, the one trick physics offers to soften the blow, only makes the failure more personal. The traveller survives, everything they love does not. And the galaxy, astonishingly, was still only the beginning. Because beyond the local group, beyond Andromeda, beyond the handful of small satellite galaxies gravitationally bound to our own, lies a universe so vast that even the distances we have discussed so far, the distances that already shattered the fantasy, are going to start looking almost quaint. What comes next does not merely make light speed feel slow, it introduces something far worse. A phenomenon that makes light speed structurally irrelevant, not just inadequate, but defeated by the architecture of the cosmos itself. The universe is not only enormous, it is expanding, and it is expanding faster than light can cross it. The local group took 10 million years, 10 million years at the speed of light, to cross the small family of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller companions. That was the distance that forced time dilation to reveal its true nature, not as a solution but as a disguise. The traveller survives, but the universe outside ages the full duration, and 10 million years was still our immediate neighbourhood, the cosmic equivalent of stepping out the front door and looking down the street. What lies beyond the local group is the rest of the street, then the city, then the country, then the continent. And every single step outward makes the speed of light feel slower, more helpless, and more obviously inadequate for the scale of the thing it is trying to cross. The Virgo cluster sits approximately 54 million light-years from Earth. It is one of the nearest major galaxy clusters, a gravitationally bound swarm of over 1,300 individual galaxies concentrated in a region of space, roughly 15 million light-years across. Some of these galaxies are enormous elliptical giants containing trillions of stars. Others are small, irregular dwarfs. Together they form a dense knot in the fabric of the cosmos, a cosmic city where galaxies crowd together, interact, merge and reshape one another through gravitational forces playing out over billions of years. Our own local group sits on the outskirts of the Virgo cluster's gravitational influence, slowly falling toward it at roughly 400 kilometers per second. At the speed of light, reaching the center of the Virgo cluster would take 54 million years. To feel that timescale, consider what Earth looked like 54 million years ago. The dinosaurs had already been extinct for roughly 12 million years, wiped out by the asteroid impact at the end of the Cretaceous period. The planet was deep in the Eocene epoch. The continents were still drifting toward their modern positions. The first ancestors of modern primates were just beginning to appear, tiny, tree-dwelling creatures with grasping hands and forward-facing eyes that would eventually lead, through an unbroken chain of evolution spanning those entire 54 million years, to you. The Himalayas were beginning to rise as the Indian subcontinent collided with Asia, a collision so slow it is still happening today. The Atlantic Ocean was significantly narrower than it is now. If you had launched a beam of light from the Virgo cluster at that moment in Earth's history, aiming it directly at our position in space, that light would be arriving right now, tonight, at the speed of 300,000 kilometers per second, having travelled without interruption for 54 million years. The photons reaching our telescopes from Virgo cluster galaxies left their sources in a world that would have been completely unrecognizable to any modern human. 54 million years of geological upheaval, biological evolution, and climatic transformation separate the moment those photons departed from the moment they reach a detector on Earth. That is the travel time to the nearest major galaxy cluster. That is what the speed of light buys you across the first step into the wider universe. Now, step further out. The Virgo cluster is itself only one component of a much larger structure. Our galaxy, our local group, and the Virgo cluster all belong to a vast gravitational basin called the Laniakea supercluster. Identified in 2014 by a team led by astronomer Brent Tully, Laniakea spans roughly 500 million light-years across and contains more than 100,000 galaxies. Its name comes from Hawaiian and means immense heaven, and for once the poetry does not exaggerate. Laniakea is not a tightly bound structure like a galaxy cluster. It is a looser collection of clusters and groups, all flowing together under the gravitational influence of an enormous concentration of mass called the Great Attractor. Everything within Laniakea, including us, is falling toward this attractor at hundreds of kilometers per second, drawn by a gravitational pull that extends across hundreds of millions of light-years. At the speed of light, crossing Laniakea would take 500 million years, Think about what that timescale means for the planet beneath your feet. 500 million years ago, Earth was in the midst of the Cambrian explosion, the sudden and dramatic proliferation of complex animal life in the fossil record that transformed the planet's biology forever. Trilobites swarmed the shallow oceans by the billions. The first vertebrates, tiny, jawless, soft-bodied creatures, were just beginning to appear. Life had not yet left the sea. No plants grew on land, no insects buzzed through the air, no amphibians crawled across the mudflats, no reptiles basked on rocks, no birds flew. The continents were arranged in a configuration utterly unlike anything on a modern globe, clustered near the equator in a geography that no map you have ever seen would depict. 500 million years is roughly 1/9 of the entire age of the Earth, 1/9 of our planet's total existence. And that is the time it takes light, moving at the fastest speed in the universe, to cross one single supercluster. One structure among millions of similar structures arrayed across the observable cosmos. Beyond Laniakea, the universe reveals its grandest and most haunting architecture. Superclusters are not scattered randomly through space like marbles dropped on a floor. They are arranged in a vast, interconnected network that astronomers call the cosmic web. Imagine a three-dimensional scaffolding of unimaginable scale. Dense filaments of galaxies stretch across hundreds of millions of light years, connecting massive cluster nodes like bridges between cosmic cities. Where multiple filaments intersect, enormous galaxy clusters form, gravitational crossroads where thousands of galaxies concentrate and interact. Between these filaments lie cosmic voids, enormous regions of nearly empty space, some stretching 300 million light-years or more across, containing almost no galaxies at all, just faint traces of dark matter and sparse wisps of intergalactic gas. The cosmic web is the largest pattern of organization in the known universe, a structure so vast that individual galaxies, each containing hundreds of billions of stars, are reduced to mere points along its filaments. And its scale makes everything discussed so far look parochial. To understand what this architecture means for a lightspeed traveler, imagine crossing one of the voids between filaments. You leave a galaxy cluster behind, one of the dense nodes where thousands of galaxies congregate, and you aim your ship at the next cluster, 300 million light-years away across a cosmic void. For 300 million years, you fly at maximum speed through a region of space that contains almost nothing. No stars, no planets, no gas clouds dense enough to scatter a headlight beam. The occasional dwarf galaxy drifts past in the darkness, a small, faint scattering of a few billion stars, so dim and so isolated that it might as well be a campfire in the middle of an ocean. Between these rare encounters, there is nothing to see, nothing to hit, nothing to measure, just the faint hum of the cosmic microwave background and the growing realization that the void you are crossing is so large that your light-speed ship, traveling at 300,000 kilometers per second, every second of every day for 300 million years, has not yet reached the other side. Galaxies are not scarce because matter is rare in the universe. They are scarce because the structures they occupy, the filaments and nodes of the cosmic web, are separated by absences so enormous that even light takes hundreds of millions of years to cross them. The filaments of the cosmic web can stretch for 1 billion light-years or more. Walls and sheets of galaxies extend across distances that exceed what standard cosmological models initially predicted would be possible. The Hercules Corona Borealis Great Wall, detected through mapping the distribution of distant gamma-ray bursts, may extend up to 10 billion light-years across, making it one of the largest coherent structures ever identified. Light itself would need 10 billion years to cross it. That is roughly 3/4 of the entire current age of the universe, consumed by a single crossing of a single structure. And the universe that contains all of these structures, every filament, every void, every supercluster, every galaxy cluster, every galaxy, every star, every planet, is measured by a single staggering number. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, spans approximately 93 billion light-years from one edge to the other. 93 billion, not million. Billion. The distance is so immense that writing it out in kilometers would produce a number requiring 24 digits. It is so vast that the Laniakea supercluster, 500 million light-years across and containing more than 100,000 galaxies, occupies less than 1% of the observable universe's diameter. Laniakea, that immense heaven, is a speck. The Virgo cluster is a speck within the speck. The local group is a speck within the speck within the speck. And our galaxy, the Milky Way, with its hundreds of billions of stars and its 100,000 light-year diameter that already defeated light speed in any human sense, is so small within this hierarchy that it vanishes from relevance entirely. But here is where something strange emerges from the numbers. Something that should stop you in your tracks. The universe is approximately 13.8 billion years old. Light has had 13.8 billion years to travel since the Big Bang. If you asked a reasonable person how far light could have travelled in that time, they would say 13.8 billion light years. And if you asked them the maximum possible diameter of the region we could observe, they would double that number and say roughly 27.6 billion light years. That answer is logical. It is intuitive. It is also completely wrong. The observable universe is not 27.6 billion light-years across. It is 93 billion light-years across, more than 3 times wider than the speed of light, and the age of the universe should permit. The numbers do not add up. Something has been stretching the distances while the light was in transit. Something has been quietly, relentlessly moving the goalposts farther apart during the entire 13.8 billion year journey. That something is the expansion of space itself. And this is where the story of light speed takes its most devastating turn. The universe is expanding. This is not a theory awaiting confirmation. It is one of the most thoroughly verified observations in all of science, supported by nearly a century of independent measurements using supernovae, galaxy redshifts, baryon acoustic oscillations, and the cosmic microwave background. In 1929, Edwin Hubble published measurements showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it recedes. This relationship, now called the Hubble-Lemaitre law, was the first direct observational evidence that space itself is stretching. The key phrase in that sentence is space itself. The galaxies are not flying apart through a fixed, unchanging space, the way shrapnel flies outward from an explosion. There is no center of the expansion. There is no edge. The space between every pair of gravitationally unbound objects is literally growing. New space is continuously and uniformly being created between galaxies, pushing them apart without either one of them moving through its local space at all. Every galaxy is approximately stationary in its own neighborhood, but the neighborhoods themselves are getting farther apart. This distinction is critical, and it is where most people's intuition fails. Einstein's special theory of relativity sets a firm speed limit. Nothing with mass can travel through space faster than light. No signal, no information, no particle can exceed the speed of light in a local reference frame. That law is absolute and has never been violated. But the expansion of space is not motion through space. It is a change in the geometry of space itself. The fabric of space-time is stretching, and it carries galaxies along with it the way the surface of an inflating balloon carries dots painted on its surface. The dots do not move across the rubber. The rubber between them grows, and there is no law of physics that prevents the rubber from growing faster than any signal can cross it. This means that the recession velocity of a distant galaxy, the speed at which it appears to move away from us due to the cumulative expansion of all the space between us, has no upper limit. For nearby galaxies, the recession velocity is modest. A galaxy 10 million light-years away recedes at roughly 227 kilometers per second, far below the speed of light, easily outpaced by a photon. But the relationship is linear and relentless. Double the distance, double the recession velocity, triple the distance, triple the speed. A galaxy 100 million light-years away recedes 10 times faster. A galaxy 1 billion light-years away recedes 100 times faster. At a certain critical distance, somewhere around 14 billion light-years in current cosmological models, the cumulative expansion of all the intervening space adds up to a recession velocity equal to the speed of light. Galaxies at that distance are receding from us at exactly 300,000 kilometers per second. They are retreating at the same speed that our fastest possible signal approaches them. A photon sent in their direction would make progress at first, but would find the remaining distance stubbornly refusing to shrink. It would be running on a treadmill, matching the belt speed, going nowhere. And galaxies beyond that distance are receding faster than the speed of light. Not slightly faster, not ambiguously faster, dramatically, unequivocally, measurably faster. The most distant objects currently visible in our telescopes, galaxies whose light has been travelling toward us for over 13 billion years, are at this moment receding at more than 3 times the speed of light. The cosmic microwave background radiation, the oldest light in the universe, released when the cosmos was only 380,000 years old, originated from a region of space that is now roughly 46.5 billion light-years away, and is currently receding from us at approximately 3.3 times the speed of light. We can still see these objects because their light began its journey billions of years ago when they were much closer and receding much more slowly. The photons were emitted in our direction, began their long swim toward us, and have been gradually gaining ground despite the relentless stretching of space beneath them. But photons emitted today from those same objects will never reach us. The space between us is now expanding too rapidly. Those photons are swimming upstream against a current they can never overcome. They will travel at 300,000 kilometers per second for the remainder of cosmic time and never close the gap. This is not a technical detail buried in the footnotes of a cosmology textbook. This is the death of the fantasy, because it means that the speed of light, the absolute cosmic maximum, the fastest speed that any object, any particle, any signal in the universe can achieve, is structurally too slow to overcome the expansion of space at large distances. Light emitted toward us from beyond a certain distance will never, under any circumstances, regardless of how long the universe continues to exist, regardless of how patient the photon is, reach us. That distance has a name. It is called the cosmic event horizon. It is not a physical barrier. There is no wall, no membrane, no visible boundary in space. It is a mathematical surface defined by the point at which the expansion of intervening space exactly matches the speed of an incoming photon. Inside the horizon, photons gain ground. They swim against the current and slowly, over billions of years, close the distance. Outside the horizon, they lose. The current is too strong. They swim at full speed and fall behind. The cosmic event horizon currently sits at a proper distance of approximately 16 billion light-years from Earth. Any galaxy closer than 16 billion light-years could, in principle, still be reached by a signal travelling at the speed of light if that signal were sent today. A photon dispatched from Earth at this moment, aimed at a galaxy 15 billion light-years away, would battle against the expanding space between here and there, and, after an extraordinarily long journey measured in tens of billions of years, eventually arrive. The photon would lose ground at first as the space between it and its target continued to expand, but gradually, as it moved into regions where the recession velocity fell below light speed, it would begin to gain. Slowly, agonizingly, the gap would close, but any galaxy beyond 16 billion light-years is permanently and irrevocably out of reach. The space between us and that galaxy is expanding faster than light can cross it. A photon sent in that direction today would make initial progress, but would gradually lose ground as the accelerating expansion of space overwhelmed its forward motion. The gap between the photon and its target would grow, not shrink, with every passing year, every passing century, every passing eon. Eventually, the photon would find itself farther from its destination than when it started, not because it lost speed. It cannot lose speed, but because the space it was trying to cross was growing faster than it could traverse. The photon would fly at 300,000 kilometers per second for all of eternity and never arrive. It is not a matter of patience. It is not a matter of waiting long enough. The destination is structurally, permanently, mathematically unreachable, even by light, even by the fastest thing the universe contains. Now consider what this means for the observable universe as a whole. The observable universe has a radius of roughly 46.5 billion light-years. The cosmic event horizon sits at roughly 16 billion light-years. Everything between 16 and 46.5 billion light-years away can be seen, because its ancient light had enough of a head start to reach us. But it can no longer be reached by any signal sent today. We can see those galaxies. We can photograph them. We can measure their light and study their properties. But we can never touch them, visit them, communicate with them, or influence them in any way. They are visible but unreachable, present in our telescopes, but absent from our future. The numbers are staggering. Because volume scales with the cube of radius, the vast majority of the observable universe lies beyond the event horizon. Approximately 94% of the galaxies we can currently observe are already permanently beyond our reach. 94%. Stop and absorb that number. Of all the hundreds of billions of galaxies whose ancient light fills our telescopes, whose images we have catalogued and studied and named, only about 6% are close enough that a signal sent today at light speed could ever reach them. The remaining 94% are already gone in every practical sense, not destroyed, not vanished from existence, simply receding so fast that no signal, no beam of light, no influence of any kind sent from Earth today will ever arrive at their location. They exist, they shine, they contain hundreds of billions of stars and presumably trillions of planets and possibly life and possibly intelligence. But they are as permanently isolated from us as if they occupied a separate universe entirely. We can see them, we can study them, we can admire their beauty in telescope images, but we will never for the rest of eternity touch them. And the situation is getting worse with each passing moment. The expansion of the universe is not merely continuing at a steady pace, it is accelerating. In 1998, two independent teams of astronomers made what may be the most unexpected discovery in the history of cosmology. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both studying a particular type of exploding star called a Type 1a supernova. These supernovae always explode with roughly the same intrinsic brightness, which makes them useful as cosmic distance markers. By measuring how dim they appear from Earth, astronomers can calculate how far away they are. Both teams expected to find the same thing, that the expansion was gradually decelerating under the collective gravitational pull of all the matter it contains. A universe full of matter should be losing momentum, like a ball thrown upward that gradually slows before falling back. Every physicist assumed the only question was how quickly. Both teams found the opposite. The expansion was not slowing down, it was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than a decelerating universe would place them. The universe was accelerating apart. The discovery was so shocking that both teams initially suspected errors in their data. When they confirmed each other's results independently, the finding earned the Nobel Prize in Physics in 2011. Something is pushing the fabric of space apart with ever-growing force. That something has been named dark energy, and it constitutes approximately 68% of the total energy content of the universe. It is the dominant component of reality. We do not know what it is. We do not understand its origin or its mechanism. We cannot detect it directly with any instrument ever built. But its effects on the expansion of space are unmistakable, measurable, and devastating for any hope that light speed might eventually prove sufficient. Because the expansion is accelerating, the cosmic event horizon is shrinking. Not rapidly, not dramatically, but steadily and irreversibly. Each year, galaxies that were previously just inside the event horizon cross beyond it, slipping out of our possible future forever. Approximately 160 billion stars, spread across uncounted galaxies, cross beyond the cosmic event horizon every single year. That is 160 billion stars per year disappearing from the volume of space we could ever hope to influence. They do not wink out of our sky immediately. We will continue to see their light for billions of years as the ancient photons they emitted long ago continue arriving. But the galaxies themselves, as they exist right now, are already beyond salvation. Every year, the reachable universe gets a little smaller, and the unreachable universe gets a little larger. In the distant future, roughly 100 billion years from now, the accelerating expansion will have carried virtually every galaxy in the observable universe beyond the cosmic event horizon. The sky will empty. One by one, galaxy by galaxy, the lights will go out, not because the galaxies cease to exist, but because the space between them and our location will have expanded beyond the reach of their light. The only structures that will remain visible to observers in what was once the Milky Way will be the galaxies of the former local group, by then long since merged into a single giant elliptical galaxy drifting through an apparently empty cosmos. The cosmic microwave background radiation, that faint afterglow of the Big Bang that currently fills every cubic centimetre of space, will have been stretched to wavelengths so incredibly long that no conceivable instrument could detect it. The evidence for the Big Bang itself will have been erased. A civilization arising in that distant era would look out at a sky containing a single galaxy surrounded by perfect, unblemished, infinite darkness. They would have no evidence that other galaxies had ever existed, no evidence that the universe was expanding, no evidence that a Big Bang had ever occurred, no evidence that the cosmos had once teemed with trillions of galaxies full of stars and planets and possibly life. They would live in a universe that had systematically, methodically, irreversibly erased its own history. Think about what those future scientists would conclude. They would study their single galaxy and develop physics and chemistry and astronomy. They would be brilliant. They would be rigorous. And they would be profoundly, inescapably wrong about almost everything beyond their own galaxy's edge. They would conclude that the universe consists of one galaxy surrounded by infinite, static, empty space. They would see no expansion, because there would be nothing left to watch recede. They would find no cosmic microwave background, because its wavelength would have stretched beyond detection. They would develop no Big Bang theory, because every piece of evidence that once supported it would have been carried beyond the cosmic event horizon and erased from their observable reality. If one of their cosmologists proposed that the universe had once been hot and dense and filled with trillions of galaxies, the others would dismiss the idea as unfounded speculation. There would be no data to support it. The universe would have hidden the evidence so thoroughly that no conceivable instrument could recover it. The truth would be out there, beyond the horizon, real and shining and full of galaxies. But no signal from that truth could ever reach them. They would live and die believing in a cosmos far smaller, far simpler, and far lonelier than the one that actually exists, and they would never know they were wrong. That is the power of cosmic expansion. It does not merely separate objects. It erases the evidence that those objects ever existed. It is a universe that hides itself from its own inhabitants, a cosmos that buries its own history behind an event horizon that even light, the fastest and most persistent messenger in all of physics, could not overcome. This is what cosmic expansion does to the speed of light. It does not merely make the universe large, it makes the universe actively hostile to the speed of light. Space is not a passive container through which light travels. Space is a dynamic, growing, accelerating medium that stretches the distances faster than light can close them. At small scales, within our galaxy, within our local group, the expansion is negligible. Gravity holds local structures together and the distances remain stable. But at large scales, beyond the gravitational bonds of our local neighbourhood, expansion wins. It always wins. And the speed of light, the cosmic maximum, the fastest velocity physics permits, becomes not just insufficient but irrelevant. Think of it like a kayaker paddling upstream on a river. Near the shore, where the current is gentle, the kayaker makes easy progress. Farther out, where the current strengthens, progress slows, and at a certain distance from shore, the current flows faster than the kayaker can paddle. From that point onward, no amount of effort will bring the kayaker closer to the opposite bank. They will paddle at full strength, at the maximum speed their arms can produce, and the river will carry them backward. The cosmic event horizon is that point in the river where the current matches the paddle speed. Beyond it, even the fastest paddler in existence is carried away. Light is the fastest paddler in the universe, 300,000 kilometers per second, 7.5 laps around the Earth in the time between heartbeats, and the river of expanding space carries it backward at the largest scales. Not because light is slow, light is the fastest thing there is, but the river is faster. At the start, the speed of light conquered the solar system in hours and stumbled only at the nearest star. Then it failed to cross even our own galaxy in any meaningful human time frame, and time dilation was revealed not as a rescue, but as a one-way ticket to a future where everything familiar has been erased. And now, Light speed has encountered something far worse than distance and far worse than time. It has encountered a universe that actively and continuously expands faster than it can move. 94% of the observable cosmos is already beyond its reach. The cosmic event horizon is tightening. Approximately 160 billion stars per year are slipping beyond the boundary that even photons, traveling at the absolute maximum speed the universe permits, cannot cross. The fastest thing in existence is being outrun by the medium it travels through. And yet, after all of this, after the solar system and the stars and the galaxy and the superclusters and the voids and the expanding cosmos, we are still asking the wrong question. We have been asking whether the speed of light is fast enough to reach distant places. The answer, as this entire journey has now demonstrated beyond any reasonable doubt, is no, not even close. But the deeper question, the one that transforms this story from a catalogue of staggering numbers into something that changes how you see the universe, is what it means, what it tells us about the cosmos, what it reveals about our place within it, what it says about a cosmos whose own maximum velocity cannot keep pace with its own dimensions, and what that reveals about existing inside such a mismatch. The distances have told their story. What remains is what those distances mean, and that is where we go next. We started this journey with a fantasy. The fantasy that the speed of light, the absolute maximum velocity the universe permits, would be enough. That if we could somehow match 300,000 kilometers per second, the cosmos would open up. The stars would become destinations, the galaxies would become neighborhoods, and the terrible loneliness of a single species on a single rock orbiting a single star would dissolve into the freedom of a universe made accessible by its own fastest speed. We granted the impossible. We imagined a traveler moving at light speed, the full, uncompromised, absolute maximum, and we aimed them at the cosmos to see what would happen. What happened was not a triumphant conquest of distance. It was a slow, methodical, escalating demolition of the fantasy at every scale we tested. Each stage of the journey dismantled another layer of the illusion, and each layer revealed a universe larger and more indifferent to the speed of light than the one before. Not because light speed is slow. On any scale that a human body has ever occupied, light speed is staggeringly, incomprehensibly fast. It circles the Earth 7.5 times per second. It bridges the gap to the moon in barely more than a heartbeat. It reaches the sun in 8 minutes. It crosses the orbits of the outer planets in an afternoon. It makes the solar system, with all its worlds and moons and drifting ice, feel like a room you could stroll across. On every scale that humans have directly touched, the speed of light is so overwhelmingly fast it might as well be infinite. But the universe does not operate on the scales that humans have touched. The universe operates on scales that make the solar system invisible, scales that make the galaxy feel small, scales that stretch so far and so wide that even the cosmic microwave background, the oldest light in existence, has not finished crossing them. And it is on those scales that the fantasy of light speed as a tool for reaching the cosmos collapsed, piece by piece, at every level we tested. The nearest star took 4 years. The galaxy took 100,000. The nearest large neighbouring galaxy took 2.5 million. The local group took 10 million. The nearest major galaxy cluster took 54 million. The Laniakea supercluster took 500 million. And the observable universe, the entire visible cosmos from edge to edge, spans 93 billion light-years across a void so enormous that 94% of it is already permanently unreachable even by light itself. At each step, the speed of light delivered the same experience. Locally it felt infinite. Cosmically, it was exposed as painfully, shockingly slow, not because it changed. Light never changes. It always moves at exactly the same velocity, in every frame, in every direction, without exception. The speed did not shrink. The universe was simply larger, and at each new scale, the mismatch between maximum speed and actual distance grew more devastating. Time dilation was the last hope, the idea that a traveller moving at nearly the speed of light could compress the experienced journey time through the physics of special relativity. And it works. Technically, precisely, measurably, it works. A traveler at 99.9999% of the speed of light could, from their own perspective, cross the entire Milky Way in roughly a century and a half. They could reach Andromeda in a few thousand years of personal time. They could, in principle, traverse billions of light years while aging only decades. The mathematics is clear. The physics is settled. It works. But what time dilation actually delivers is not travel. It is exile. Consider what it truly means, in human terms, to cross the Milky Way using extreme time dilation. You board the ship. You say goodbye to everyone you have ever known, understanding with full clarity that you will never see any of them again. Not because they will forget you, because they will be dead before your ship reaches cruising speed. You accelerate to a velocity so close to the speed of light that the difference between your speed and the speed of light can only be expressed in a string of nines after a decimal point. Your onboard clock begins to slow. Your heart beats at a rate that, from the perspective of an observer outside the ship, appears glacial. Chemical reactions in your cells proceed in what an external observer would describe as agonizing slow motion. Neurons fire at a fraction of their normal rate. You experience time normally from your own perspective. A second still feels like a second. A meal takes as long as a meal has always taken. A thought forms at the usual pace. But outside the walls of your ship, the universe is racing forward at its full, relentless speed. While you eat a single breakfast, a full generation passes beyond the walls of your ship. Children born the morning you sat down have grown into adults with families before you finish eating. While you sleep through a single night, an entire human lifetime unfolds in the world outside. Someone is born, grows old, and dies in the pause between your eyes closing and opening. Centuries of history play out while you read a book. Civilizations rise on distant worlds, build monuments that endure for generations, wage wars that reshape continents, achieve peace that lasts for ages, and then crumble into dust and silence. All just before you turn the page. The galaxy rotates beneath you. The spiral arms shift their positions. The constellations visible through your windows rearrange themselves because the stars have moved measurably during your transit, and some of them have ceased to exist entirely. Their fuel exhausted, their light extinguished while you were brushing your teeth. You arrive at the far side of the galaxy. Your shipboard clocks say you have been travelling for perhaps 150 years, a span that might be covered by several relay crews or by some speculative technology of extended lifespan. You step off the ship. The calendar outside reads 100,000 years in the future. Everything you left behind is gone, not merely changed, not merely aged, obliterated by the passage of time so complete that even the memory of your civilization has likely been lost and rediscovered and lost again dozens of times over. The language you speak has been dead for tens of thousands of years. The nation that funded your mission collapsed before your ship cleared the outer spiral arm. The culture you belong to has been studied by archaeologists of civilizations that have themselves become archaeological subjects for still later civilizations. The people you loved did not merely die. Their descendants lived and died and had descendants of their own who lived and died for 100,000 years. The genetic lineage that connected you to your home world branched and diverged so many times that no one on Earth, if anyone remains there, shares any meaningful kinship with you. If you turned the ship around and flew back at the same speed, another 100,000 years would pass in the outside universe. The round trip consumes 200,000 years. You would return to an Earth that has aged longer than the entire existence of Homo sapiens. Nothing would remain. No language, no institution, no building, no monument, no archaeological trace of anything you ever knew. The planet might still orbit the sun. It might still support life, but it would not be your planet. It would be a stranger's world, populated by whatever species or successor has emerged in the intervening ages. You would be an alien, visiting an alien world that happens to occupy the same orbit your home once did. This is what time dilation offers. Not a shortcut, not a solution. An exile from everything that still existed the moment you departed. It compresses your experience of the journey, but does absolutely nothing to the journey itself. The galaxy is still 100,000 light-years across. The distance is unchanged. The time required for anything outside your ship to unfold is unchanged. The universe stays exactly as large as it always was. You are the only thing that changes inside it. The traveler survives. The meaning of the journey does not. And yet, even time dilation, with all its staggering cost, cannot rescue the traveler from the largest structure in the story. The expansion of space. Beyond the local group, the universe is growing faster than any ship can cross it, faster than any photon can bridge it. The cosmic event horizon sits at roughly 16 billion light-years from Earth, and it is contracting every year as the accelerating expansion of space carries more and more galaxies beyond the boundary of the reachable. No amount of time dilation can overcome the expansion of space, because time dilation compresses the traveler's experienced time, not the universe's geometry. If the space between you and your target is growing faster than you can traverse it, no manipulation of your personal clock, no compression of your experienced duration will bring you any closer. You will fly at maximum speed, experience whatever compressed time span the Lorentz factor provides, and still find yourself farther from your destination with each passing moment. The current will carry you backward no matter how fast your arms move, and the current is getting stronger. 94% of the observable universe is already beyond this boundary. 94% of every galaxy we can photograph, every quasar we can detect, every cosmic structure we have ever mapped with any instrument is permanently and irrevocably beyond the reach of light, beyond the reach of any signal, beyond the reach of any traveler, regardless of their speed or their technology or their willingness to sacrifice everything they know to the cold mathematics of time dilation. Not in a million years. Not in a billion years. Not in an infinite number of years. The expansion of space has drawn a line, and light, the fastest messenger the universe possesses, stands on the wrong side of it for 94% of the visible cosmos. Every year, roughly 160 billion more stars cross that line. Every year, the reachable universe shrinks by a sliver, and the unreachable universe grows. The expansion did not ask permission. It does not care about our ambitions. It won before our species learned to look up. Now consider the oldest light in the universe. The cosmic microwave background radiation. It was released approximately 380,000 years after the Big Bang, at the moment when the universe cooled enough for the first stable atoms to form, and the cosmos became transparent for the first time. Before that moment, light could not travel freely. The universe was a dense, opaque fog of particles and energy, so hot and so thick that photons scattered off free electrons after traveling only microscopic distances. Then, in a transition that unfolded across the entire universe simultaneously, the fog cleared. Electrons bonded with protons to form hydrogen atoms. The scattering stopped, and light, for the first time in cosmic history, was free to travel. Those photons, the first photons to ever travel freely through the universe, are still traveling now. They have been in transit for 13.8 billion years. They left their origin when the universe was an infant, a glowing fog of cooling hydrogen just beginning to clear. They have watched, in a manner of speaking, everything that has ever happened unfold around them. The first stars ignited while they were already in transit. The first galaxies assembled while they were still flying. Our own Milky Way formed, matured, developed spiral arms, consumed smaller galaxies, and settled into its current structure while those photons were still crossing the void. The sun formed from a collapsing cloud of gas and dust, approximately 4.5 billion years ago, and those photons had already been travelling for more than 9 billion years before our star even existed. Life emerged on Earth, evolved through billions of years of increasing complexity, produced intelligence, produced civilization, produced telescopes, and those photons were still in transit. They are arriving at Earth at this exact moment, at a density of roughly 411 photons per cubic centimetre of space. They fill every room, they pass through every wall, they surround every person on the planet. They are the oldest light in existence, and they have been flying at 300,000 kilometres per second, without interruption, without slowing, without pause, for nearly 14 billion years. The region of space they originated from now lies roughly 46 billion light-years away, carried to that immense distance by the expansion of the cosmos during their inconceivably long journey, and they are only just now arriving, Think about what that means for light speed. The universe created these photons at the earliest possible moment. It sent them outward at the fastest possible speed, and they've been traveling for 99.997% of the entire age of the universe. They are the most senior travelers in existence, and they have only covered a finite portion of the observable universe. They crossed roughly 46 billion light-years of expanding space, but the observable universe is 93 billion light-years across. Even the oldest photons, traveling since the beginning of time, have not crossed the whole thing. Light itself, born at the dawn of the cosmos and traveling at the absolute maximum for almost 14 billion years, has not finished the job. That is the fact that transforms this story from a lesson about large numbers into something more profound. The speed of light is not a human limitation. It is a cosmic one. The universe did not build a speed limit that only punishes us. It built a speed limit that punishes itself. Its own light, launched from its own origin, travelling at its own maximum speed for its own entire lifetime, has not been fast enough to make the cosmos fully connected. Regions of the observable universe have never been in contact with each other. Photons from one side have not reached the other. The universe is so large that its own messenger, the fastest thing it contains, cannot deliver a message across the full breadth of the house it lives in. Not in 14 billion years. Not ever, given the accelerating expansion that is now stretching the distances faster than the messengers can close them. We are not slow. That is the realization that this entire journey, from the first second of light circling the Earth to the last photon swimming against the current of expanding space, has been building toward. We are not slow. Our spacecraft are slow by cosmic standards, yes. Our biological lifetimes are brief beyond measure on cosmic timescales, certainly. Our technology is primitive by any standard that would matter for interstellar travel, without question. But the speed of light is not our speed. It is not a human invention or a human limitation. It is the universe's speed. It is the absolute maximum, the ceiling of all velocity, the fastest thing that exists or can ever exist in this cosmos. And for 45A, and it is too slow, not too slow for us, too slow for the universe. The cosmos built the fastest possible thing, and then built a house so vast that the fastest possible thing cannot cross it. This is not a story about human inadequacy. It is a story about cosmic architecture, about a universe designed, or at least structured, on scales so enormous that its own fundamental laws of physics cannot bridge the distances within it. The speed of light is not a barrier between humanity and the stars. It is a barrier between the universe and itself. Light speed feels infinite because our environments are small. This is the key to the entire story. Stand on the surface of the Earth and watch light circle the globe 7.5 times per second, and you will believe, with every instinct your evolution provided, that this speed can reach anything. It looks limitless. It feels godlike. It appears to erase distance the way a flood erases footprints. And within the narrow confines of a human life lived on the surface of one small planet, orbiting one average star, in one quiet arm of one spiral galaxy, it effectively is limitless. Light speed handles every distance a human has ever personally encountered, with such effortless, instantaneous authority that the idea of it being insufficient seems absurd. You flick a light switch and a room illuminates instantly. You look at the moon and see it as it was 1.3 seconds ago, a delay so small you cannot perceive it. You look at the sun and see it as it was 8 minutes ago, a delay so modest it never occurs to you that you are looking into the past. But zoom out. Step beyond the solar system. Step beyond the nearest star. Step beyond the galaxy that contains you, and the cluster that contains your galaxy, and the supercluster that contains the cluster. Look at the cosmic web stretching across hundreds of millions of light years. Look at the observable universe spanning 93 billion light years from edge to edge. And the same speed that circled the Earth 7 times in a heartbeat, the same speed that felt like the answer to everything, becomes a crawl. Not because the speed changed. The speed never changes. Because the canvas it was trying to cross turned out to be incomprehensibly, absurdly, almost impossibly large. The speed did not change. The scale did, and the scale won. Every structure in the universe is an expression of this mismatch between speed and scale. The fact that galaxies are separated by millions of light years is not an arbitrary design choice. It is a direct consequence of how much faster the cosmos can grow than information can travel through it. The fact that the cosmic microwave background, born at the very beginning of transparent time, is only now arriving, from regions 46 billion light-years away, is a measure of how thoroughly the expansion of space has outpaced the motion of light through space. The fact that 94% of the observable universe is unreachable is a statement, written in the geometry of space-time itself, about how completely the growth of the cosmos has defeated its own speed limit. Every one of these facts is a variation on the same underlying theme. The universe is too large for its own fastest speed. The house is too big for the messenger. There is a quiet terror in this understanding. The idea that nothing we could ever build, no technology, any civilization, anywhere in the cosmos could ever develop, no act of engineering genius or physical desperation can overcome the fundamental mismatch between the speed of light and the scale of the universe it inhabits. The speed limit is not a challenge waiting to be overcome by cleverness or persistence. It is a structural feature of reality, as immovable as the geometry of space-time itself. Even the universe cannot break its own rules. Even the cosmos cannot send a photon faster than 300,000 kilometers per second, and at that speed, most of its own contents are out of reach. Every star we see in the night sky sends its light toward us at maximum speed, and many of those photons have been traveling for centuries or millennia or millions of years. Every galaxy in our telescope sends its light at the same maximum speed, and those photons have been traveling for millions or billions of years. The universe is constantly broadcasting at the highest volume its physics allows, and the messages still take eons to arrive. That is how large the cosmos is. Not large relative to us, not large relative to our technology, large relative to light, large relative to the fastest thing that can ever exist. But there is something else in this realization, something quieter than terror and more lasting than despair. There is awe. The universe did not have to be this large. There is no law of logic that required the cosmos to stretch 93 billion light-years across. There is no mathematical principle that demanded galaxies be separated by millions of light-years of expanding void. The universe could have been smaller. It could have been compact enough for light to cross in a human lifetime. It could have been a cozy, navigable, intimate place where civilizations on neighboring worlds could chat across the gap between stars with only modest delays, where voyages to other galaxies took decades rather than millennia, where the night sky was not a catalogue of unreachable lights, but a map of places you could actually visit. It is not that universe. It is this one, vast beyond comprehension, structured on scales that reduce even the speed of light to irrelevance, expanding at a rate that makes most of its own contents permanently inaccessible to each other. And within that vastness, on one unremarkable planet, orbiting one ordinary star in one undistinguished spiral arm of one galaxy among trillions, a species evolved that could look up at the sky, measure the distances between the stars, calculate the travel times between the galaxies, map the expansion of space, detect the cosmic microwave background radiation from the dawn of time, and understand, truly and completely understand, that the fastest speed in the universe is not fast enough to make any of it reachable. That understanding is itself a kind of miracle. We are the universe becoming conscious of its own dimensions. We are matter arranged into a pattern complex enough to comprehend the incomprehensible scale of the thing it inhabits. We cannot reach the far side of the galaxy. We cannot visit Andromeda. We cannot send a message to the Virgo cluster and expect a reply before geological time has erased the meaning of the question. We will never touch the 94% of the observable cosmos that has already slipped beyond the cosmic event horizon. But we know this. We measured it. We calculated it. We wrote the equations and built the instruments and pointed them at the sky and deduced, with extraordinary precision, exactly how vast the cosmos is and exactly why the speed of light cannot make it feel small. And there is something quietly astonishing about a species that can see the cage clearly, measure every bar, describe its geometry with mathematical certainty, and feel the full emotional weight of living inside it, even while knowing that it can never, ever leave. The speed of light is not the answer to distance. It never was. It is the fastest possible speed in a universe where the fastest possible speed is not fast enough. It is the ceiling of all motion, not the solution to the problem of cosmic scale. And the terrifying, beautiful, humbling truth at the end of this journey is not that we are slow. It is that the universe is so enormous, so staggeringly, relentlessly, magnificently vast, that even its own maximum speed, the fastest anything can ever move in any context under any circumstances, cannot make it feel like home, cannot make it feel reachable, cannot connect one side to the other, cannot deliver a message from its oldest light to its farthest edge in the time it has been alive. The universe is not merely bigger than light speed can handle. It is bigger than the concept of speed can handle. Distance, at the largest scales, has won a permanent victory over velocity. Light is the fastest prisoner in the universe. It is born at the maximum speed. It lives its entire existence at the maximum speed. It cannot choose to go faster. It cannot accelerate. It cannot strain against its limit. It moves at exactly 300,000 kilometers per second from the instant of its creation to the instant of its absorption. And in between, it crosses distances that take years, millennia, millions of years, billions of years to traverse. The oldest photons in existence have been traveling for 13.8 billion years at this unchanging, unbreakable maximum velocity. They have not finished crossing the observable universe. They have not even come close. The fastest thing in the universe has been running at full speed since the beginning of time, and the universe is still bigger than the distance it has covered. We began with a fantasy, the fantasy that light speed would be enough. It is not. It was never going to be. Not because we are small, though we are. Not because we are brief, though we are. But because the universe is so vast that even its own laws cannot connect it. Even its own light cannot cross it. Even its own maximum speed cannot make it whole. And somewhere in that realization, in the quiet space between the terror and the wonder, lies something that might be the most human response of all. Not despair, not surrender, but a kind of stunned, wordless respect for the sheer, incomprehensible scale of the thing we were born inside. We are here. We looked up. We measured the distances. We understood the answer. And the answer is that even light speed is not fast enough. It never was.